All right, so this talk is about the Scala.js compilation pipeline. Scala.js compiles Scala to JavaScript. My name's Tobias, and I'm one of the core contributors. This is my GitHub handle. Before we have a look on how Scala compiles to JavaScript, let's first have a look and remind ourselves how does the Scala pipeline work for Scala on the JVM. Right? So let's assume you're writing an app. You have your app Scala source file there. You feed that into the Scala compiler, and the Scala compiler will create a class file. That class file, you feed it to the JVM, and the JVM will run your application for you. Usually, you package these class files into a jar, but fundamentally doesn't really change anything. The JVM will look into your jar and get those class files out there for you. If you start using libraries, which is, I guess, something many of us do, something very similar happens on the side of the library author. Right? The library author writes a source file, feeds that into the compiler, and creates a jar. And this jar is what he publishes. Right? When you launch your application in the JVM, you give both those jars, you put them on the class path. And once you start using a class of the library, so let's, for example, say your application uses a list class of the library. When you use that class for the first time, the JVM will look on the class path and search for that list class and load it. So it's dynamically linking the class into the application. If the class is not there, you will get a class not found error, which I guess all of us have seen and are very unpleasant. I said you're using the list type in your application. So actually, you might see that there's an arrow missing here on this slide. If you write list in your app Scala file, and the compiler doesn't know about your library, it will tell you, hey, I don't know what you're talking about list here. I can't verify that what you're doing here is all right. So you actually have to put the library you're using also on the class path of the compiler, so the compiler knows about the other things you intend to use. Now, if these two arrows get out of sync, right, the one that goes from the library to the JVM and the one that goes from the library to the Scala compiler, then even though your stuff compiles properly, you will get class not found exceptions when you try to run your application. With Scala.js, this looks actually very similar. Right? There's a couple of differences. First of all, we're using the Scala.js compiler plugin. When we run the compiler, instead of emitting class files, we emitting Scala.js intermediate representation. It's a format similar to the class format, but it's tailored to Scala.js. Instead of just running these files, right, we want to produce a file, a JavaScript file, which is JavaScript coded in a single file. So we need to run this through the linker. The linker is a separate application the Scala.js project provides, and it takes all these IR files and links them together and produces a JavaScript file. And then you have JavaScript, and you run it with whatever JavaScript VM you want to run it, Node.js in the browser, Phantom.js. When you compare to the previous slide, you can see that there's a file, there's an arrow missing, right? This cross arrow here, we actually don't have it yet in this graph. So currently, if we're using the list type in app, the compiler wouldn't know about this type and would complain, right? So the easiest solution is, well, just have the compiler read Scala.js IR and figure out that there's a list type and go on from there, right? Unfortunately, the Scala compiler doesn't know about Scala.js IR, right? It hasn't been built to do that. So therefore, what we do is we emit class files as well. So the Scala.js compiler actually emits class files and Scala.js IR. The IR is used for linking, and the class files are looked for symbol lookup when you compile. All of this stuff comes packaged in a jar, and this is what you publish. So in the end, it looks very similar. There's really two key differences there. One, in the jars, you have class files and Scala.js IR files. And instead of running directly with a virtual machine, you run stuff through the linker, and then you compile to JavaScript. OK, so from here, it is actually pretty obvious that we have two key components to that whole pipeline. We have the Scala.js compiler, and we have the Scala.js linker. And I'm going to talk about these two components in order. All right. These are the phases of the Scala.js compiler. We're going to go through these phases one by one and have a look at what they do individually, and hope we're done in the half hour I have. Just kidding. Oh, this is hard to see. Only these two red guys here, two guys prefixed with JS, are phases that are actually specific to the Scala.js compiler. As I mentioned, the Scala.js compiler is really just a compiler plugin. So all the black stuff is just the Scala compiler. And the red phases are things we add. You will have a better picture in the next slide. And the red phases are things we add, right? So this actually much more looks like that. Whereas only these two guys are actually Scala.js specific. Everything else is just plain Scala compiler. So what happens here? Again, you have your source file that feeds into the compiler front end. The front end is mainly the parser and the typer. So it makes sure that, well, you have right syntax, and it makes sure that what you're doing is statically sound, so you have type safety. The front end is also the part that will potentially use a class file of a library to make sure that you're using your list type in the right way. The front end is also responsible for implicit resolution and macro expansion. All right. So we got all that. From there, we feed in the JS interrupt phase. The JS interrupt phase is mostly doing error checking of the Scala.js specific things. So if you're using facade types the wrong way or exports, doesn't matter really if you don't know what that means. It's Scala.js specific things that we check there. So we can give you nice error messages rather than just the later phase crashing and telling you, hey, I failed, sorry. Then we feed into the backend. The backend is really the part that simplifies the complex Scala syntax to the simple representation that the JVM understands. Right, so it does all kinds of, it does type erasure, it does mix-ins, it does all kinds of very fancy stuff that fortunately we don't have to take care of. From there, the path forges, right? We have the JVM phase that emits class files. I'm not going to talk about that. That's just standard how the Scala compiler does it. And we have the JS code phase that will eventually emit the Scala.js IR files. So let's look at an example. Right. This is our piece of code. This is going to accompany us through the rest of the presentation, and we're going to feed that thing through the whole pipeline until at the end, hopefully, we have JavaScript that we can actually run. So what do we have? We have a multi-alerter class. It allows us to alert the user multiple times. Very useful feature. It uses this message factory that allows it to create some hello world messages. You can see that on the bottom. And it has the multi-alert method, right? So you can give it a number. Hey, I would like to alert my user 10 times. So I'm sure he actually understood, right? It just opens up an alert box, which is basically a message box, and gives a message there, right? Are there questions about this code? Good. So when we feed this into the front end, what happens? First of all, the typer will add all the types, right? So we were lazy there, and some of the type annotations, we didn't put them there. The typer is going to add all of them. Then this for loop is expanding. So you can see there the int wrapper, that's an implicit conversion, and the for syntax is desugared into a for each. The body remains the same. And down here, the string interpolator expands to a call to the string context. That's just how internally string interpolators are implemented. All right, again, I'd like to mention this is just a Scala compiler. We get all this for free. There's no code in Scala.js at all to do this. All right, so we got from the source file into the front end, through the front end, and now we're going to the JS interrupt phase. First phase, which is actually part of the Scala compiler, of the Scala.js compiler. Excuse me. So what does JS interrupt do? It has two responsibilities. One, catch JavaScript interoperability errors. There's no error in the code I presented, so we're not going to see anything there. And exports. Exports are methods on Scala classes that JavaScript can call. Right? So we've maybe seen this JS export annotation there. It basically says, hey, I want this method to have a sensible name in JavaScript, so I can call it. Otherwise, methods will just get a very strange name. We don't give any guarantees, so you won't be able to reliably call it. The JS interoperability phase basically just does this. It adds this additional method with this fancy name. Basically says, hey, this is a JS exported method. What happens there is we're going to pass this method through the whole compilation pipeline, and in the end, we're going to catch it and see, oh, there's an exported method. We'll have to emit something special for that. Right? The reason why we propagate it through the pipeline is that, for example, you can overload exports. And when you overload exports and you might do something fancy with the types such that the erase types, they're actually ambiguous and they end up being the same type, right? And you want to prevent that. Now, Scala.c has a whole infrastructure to do that, so we want to leverage that and want to reuse it. So we just feed it into the whole pipeline, and if that happens, Scala.c will just complain, and we don't have to do anything about it. We really get it for free. That's the reason why we add these guys here. I'll show you later how we catch them and translate them into actual exports. All right. From there, just this additional method, not a lot happened. We feed, this red arrow here is actually hard to see, huh? There's a red arrow here, where we are. We feed it into the backend. And it's kind of ironic I said the backend simplifies things, but this is how it looks after the backend. So I don't expect you to understand all of this. There's just a couple of things I'd like to note. For example, the constructors, they have been lifted from the class body into a separate method. There's this thing here, an extension method pops up. An extension method is Scala.c's way of implementing mixin. So at this point, we don't have trait methods anymore. We have pure interfaces and classes. And down here, we see some very fancy stuff going on for var args. All right. But that's, again, not our job. Scala.c takes care of it. OK, so we are already ready to translate all this into the IR. Unlike all the other phases, JS code is a translation phase, right? The other phase is just take Scala's internal representation of code and transform it. The JS code phase takes this internal representation and translates it into the IR. So to better understand what it's doing, we'll have a look at the IR first, how it is, and some properties it has, so we can better understand what transformation we actually have to do. All right, so the intermediate representation of Scala.js is in AST form, in typed AST form. What does that mean? Let's have this little example of code up here. In AST form, that basically means, OK, we have a block, then we have a val_def, where the name is x, we have a literal string on the right-hand side of the assignment. We apply a function here, where we select the member on this x variable here, and we have a literal that we pass. You can see that some things that you see in the source code are abstracted here. So for example, whether you have a semicolon here or this is a new line, doesn't appear anymore in this abstract syntax tree form, which is practical because we don't really care anymore, right? Typed just means that each of these elements has a type to itself, so we know that the literal there is a string, x is a string, and so on and so forth. This is the same representation that the Scala compiler uses internally, so the translation is almost one-to-one. It's really trivial. So there's nothing special to be done there. We allow complex expressions in the AST. So for example, a block is an expression. And so the upper code there, where you have a result, and then inside you have a variable, right, a helper, and you just return this value from the block. Many languages, like JavaScript, for example, they don't allow you to do that. So you would have to write the lower code there and basically move the helper variable out. Again, that does not matter to us right now, because that's how Scala represents these internally, so we can just translate them one-to-one. Next to having normal Scala operations, like you would expect, we also support on any kind of value you have anywhere to say, hey, by the way, I want you to call this JavaScript function here on that thing. And just like JavaScript is, if the function's there, it's going to work, and if it's not there, well, it's just going to fail miserably at runtime, just like JavaScript is. This is something we'll have to take care of because Scala did definitely not foresee emitting JavaScript operations, so we need to do something special about that. So I'll mark this. What types do we have in the IR? We don't have generics, just like on the JVM. That's all fine. The Scala compiler took care for us to erase all these. We have primitive types, int, double, and so on and so forth, and we have class types. Right? So this is all like literal one-to-one translation. As far as classes and interfaces are concerned, we have single class inheritance. We have multi-interface inheritance, but interfaces are pure. So this is really just like on the JVM. We don't have overloading. We use name mangling instead. And as we've already seen a bit, is every class can also have JavaScript methods on it. Right, so these are definitely things which are different, these three guys, right? The JavaScript operations, the name mangling for overloading, I'm not going into detail there because it's pretty trivial, and the JavaScript methods. So how do we do this translation? A calling JavaScript from Scala code. Let's look at our example again, the multi-alert method. We have a for loop. We all know how that works. And then we have this thing there, DOM-alert. What's DOM there? Right? Let's have a look at the definition of DOM. DOM is just a plain object, but it extends this weird type, JS global scope. This type tells the compiler, hey, this is not actually an object. So the compiler is actually not going to emit any code for that. It's going to say, oh, this is JavaScript world. This is just a declaration. I'm assuming this stuff is there. And it says, hey, all the methods I have defined, they're actually just global JavaScript methods. So the compiler is going to translate this to this guy, right? So here you actually see an example of how we use name mangling for overloading. You see we append a couple of things there based on the types in the arguments and the return type. Then we have the for loop. I'm going to spare you that. The code looks terrible because it's basically an implicit conversion on the integer and then an extension method on the integer and then the collection library and for each. And it's terrible. And then you see that special thing here, global alert. This is how we represent calls to the JavaScript world. And down here you see the call to hello. So the interesting thing to observe here is that although we have two normal calls here, we have DOM-alert and messages hello, these calls translate to something very different here, right? The alert call translates to this guy, whereas the hello call translates to this guy. This again is just name mangling for overloading again. And this is all based on types. So this is how we can call JavaScript methods even though writing normal Scala code. All right, so how do we handle JavaScript methods on Scala classes? I said JS-interop generates this magic method here, right? If we encounter a method like that, the IR we emit looks something like that. First of all, it's just the method itself. And we emit this additional method here, the export method. Again, we use strings to represent JavaScript methods that basically checks the argument types. You can see the argument of that method is an any. So anything is allowed there, and in there we cast the argument. So this will fail if we're given something which is not an int. So we can then afterwards safely pass it to the exported method. So we can still in there assume that, oh, we actually have an int, right? This is also the part where we would resolve overloading of exports in case there were any overloading. All right, so we have IR. Nice. So this is the first part, right? So we're basically now on that jar here. We have compiled the application. Let's also assume we have compiled the library. So now let's have a look at the linker. That's this box over here. These are the phases of the linker, right? So we feed in the IR. This now is the IR of both the library and the application. This is all the IR you need, just like the class path you would have on your JVM, right? The linker assembles all the classes you need to run your application, right? So it figures out which are the classes you actually need, and it reads those files. From there, optionally, you can move it. You can run it through the IR checker. This is basically just a sanity check. It's very useful for debugging, that the IR actually satisfies the constraints you have. Otherwise, the later phases might fail, not because they're wrong, but you're giving it buggy IR. The optimizer reduces size and increases speed of the code. The refiner removes classes that, thanks to the optimizer, are not needed anymore. We will see an example of that. And the emitter finally translates the intermediate representation into JavaScript code. All right, same game again. We're going to take the IR, we're going to feed it through this pipeline and see what happens. Oh yeah, by the way, I forgot. The closure optimization thing down here is you can also feed that stuff into the Google Closure compiler to do some more that code elimination and renaming. It will just produce a smaller JavaScript file, which is good for production. The linker phase is the phase we use to call that code elimination. Now, in time, we have realized this is actually much more alive code inclusion than that code elimination. So what it does, it's looking at the entry points of the Scala.js code. So these are the exported things. And it looks at everything that is reachable from there. So from our original example, we have an export here, right? That the multi-alerted class is exported. So, oh, OK, the multi-alerted class is exported, so it's reachable. All right. If the class is reachable, that means its constructor is reachable. Okay, in the constructor, we instantiate hello factory, so hello factory is reachable. All right. Is that all? No, that's not. We also have this other export there. All right, this export is a multi-alerter, and multi-alerter is reachable. Therefore, all its exported methods are reachable. Right? If there is no instance of multi-alerter, it doesn't matter whether a method is exported or not, because there's no instance, so you can't call a method. But here, for instance, it's possible that we have an instance, right? So you say, okay, good. This multi-alert method here is reachable, right? Now, the for loop here will reach all tons of classes in the Scala standard library. I'm not going to go into that. The DOM alert call is not really there anyways, so that doesn't reach anything. And we reach the hello method in hello factory. All right, that's it. And you see automatically, without even looking at it, we have not included the hello debug method down there because no one uses it. All right? Just like concurrent hash map, for example. We also don't use it, so that's why alive code inclusion. We have not eliminated concurrent hash map. We have just not included it. All right. From there, we feed into the optimizer. Let's take that piece of code again. Right? And I have a confession to make. I actually lied to you. I told you I'm going to spare you how the for loop looks like. This is how the for loop looks like. OK, don't look at it. It's ugly. All right. The optimizer will turn this into that guy. Right? So instead of having this nasty little for loop, we just say, this is just a while loop. Just have a var and while loop. Right? The nice thing there is, well, A, this is smaller, B, it's faster, and C, it also doesn't use the Scala collections library anymore. Ha! Nice. So when you feed this into the refiner can actually now eliminate range and all these things we had in the Scala collection library because we don't need them anymore. Nice. OK. So we are ready to make JavaScript code. Again, we're at the translation step. So now we're going to do the opposite. We're going to look at the IR again and say, OK, which of these things do we have to change so that we have JavaScript in the end? Right? Which of these things are not OK for JavaScript? Trees are in AST form, in typed AST form. AST easily translates back to source code, so that's fine. We don't care about types. We just ignore them. Right? JavaScript doesn't have types. Complex expressions. I mentioned before, JavaScript does not allow complex expressions like that. So we'll have to do something about that. JavaScript operations, JavaScript tends to handle very well, so we're fine there. JavaScript doesn't know generic types, we're fine there. Primitive types, we just reuse the JavaScript primitive types, number, Boolean, and so on and so forth. Class types we can model using prototype chaining. I'm not going to go into details there. That's very heavy JavaScript land. Classes interfaces, we have single class inheritance. Right? So we're going to model single class inheritance using prototype chaining. Multi-interface inheritance, well, JavaScript doesn't know interfaces, but since it's dynamically typed, we can just actually erase interfaces because we statically know the methods are there, so we just call them. No overloading, well, lucky us, we did that because JavaScript definitely does not support overloading. And JavaScript methods and classes, that's also fine. All right, so you're actually not very far. Here the example unfortunately breaks a bit, and I have to take another piece of code to illustrate how we desugar. So we turn these complex trees into easier trees. Let's look at this a bit strange norm method. Right? It takes an integer and a string, and it converts the string into an integer in this like nested block there, and then calculates the norm, right, of these two values. And in pseudo JavaScript code, we would immediately translate that looks somewhat like that. You notice the pseudo up there because there's strange stuff in here, right? We have a return all up here that returns the whole block. And then we have this var, which also is a block is assigned to it, right, out here. That's definitely not allowed in JavaScript, right? So we'll have to push down. We call it left-hand side push down. So we have to push the return inside this block. Oh, this looks much saner already, right? But we still have the problem with this var here. So we're just going to do the same. We're going to push the var down here. All right. Some of you might object to that and say, whoa, hold on. You changed the scope of B2. right? B2 is out here, so yeah, you could use it down here, right? And now you're pushing it into there. B2 is not even defined here anymore. What are you doing? This is JavaScript. In JavaScript, unfortunately for someone who writes JavaScript, fortunately for us, vars are scoped to the enclosing function block. So as long as we're careful and we don't have names that collide and we only optimize on the function level, which we do, we can perfectly do that. So this is actually valid JavaScript code. Well, nice. All right. So we just write that to a file.
You just leave all those brackets in there.
Oh yeah, why not?
Whatever.
Yeah, it's probably the block that optimizes these away. So if you create the outer block here and you tell it, hey, you have these two statements, it will look at each statement and look at the block and say, oh, I'm actually a nested block, so I'm going to pop the inner block immediately. And if it doesn't, it's the Google Closure compiler that takes care of it. This is always our argument. If people say, hey, you're not optimizing this, well, yeah, Google Closure compiler. All right, so we write this to a file. That's straightforward. All right, so we're done. JavaScript code. This is simplified version of how we emit the JavaScript code of the Scala code. The exports are not on here, but all the rest is. Right, so the constructor here of the multi-iterator, the for loop, which is now a while loop, and the hello method here, which, yeah, I didn't go into the details of the string context. That there's a lot of instantiations of C wrappers and JavaScript arrays and whatnot. All right. I'm going to open it up for questions before I go over my shame slide. This is the shame slide because it contains all kinds of stuff I omitted, but still is actually kind of important. But questions first. Go ahead.
I was actually going to ask you about reflection.
Yep.
I was thinking of that in the alive code version specifically.
I was expecting that. OK. There you go. OK, the question was reflection. Reflection, which I retorted I was expecting that. All right. Let's look at the linker. Let's look at the linker, right? I'm going to enumerate the phases in the linker that don't like reflection. OK? The linker doesn't like reflection. The optimizer doesn't like reflection. The refiner doesn't like reflection. And as of now, the emitter is OK with reflection, but in the future might not be OK with reflection. I'm a bit going into detail why, OK? The linker, as I mentioned, assembles all the classes that are necessary to run your application. Class for name, anyone? It actually can't do that. Right? It actually can't do that. Since the JVM links at runtime, loading a class as you go through code is absolutely normal. Right? The first time you see the list type in compiled code, you say, oh, cool, list, let me load that. It's not how it works in Scala.js. So it is very hard, right, to have an ad hoc linking mechanism. It's like, hey, I want this class there. And then somehow the JavaScript code should go back and say, OK, let me grab this IR again. But where from? You don't want to ship all the IR out to your client if you're in a web browser. Because this is, we're talking megabytes there, right? I mean, the IR is, if you compile everything that is reachable, we're looking at 100 or 200 megs probably of just stuff you don't need. The optimizer, in theory, could be made to support reflection, but it wouldn't be able to optimize that well because it does things, for example, it recognizes monomorphic dispatch and polymorphic dispatch positions, things like that. So if there's only one subclass of A, even if you call it a method in A, it will see, oh, actually, this is in theory polymorphic dispatch, but I know there can only be one subclass of this thing. So this is actually monomorphic, let me inline this. Bam, faster. But if you can just load the class via reflection, that knowledge is actually doesn't hold anymore. And you would have to re-optimize that code. The JVM can do that. Well, we can't. We can't change code on the fly. The refiner is similar considerations than the linker. And the emitter, I'm not going into details.
So I guess that means that reflection is more or less off limits with Scala.js?
We're having discussions about whether we can mark things to be reflectionable, which is essentially the same to just say, hey, include this all the time, right? It's still in the early stages. We realize that there potentially will be something, that there has to be something there, but the story is really not yet clear who defines what exactly, right? If you have a type in your library, would you as a library author say, hey, I want to mark this reflectable? Or do I as a user want to say, hey, by the way, that type in that library over there, that was never intended to be used by reflection, I want this to be reflectable. And how would you specify that?
I was just curious about, actually I was more curious about methods, because methods seem to be getting renamed in certain phases, but honestly, like, you shouldn't take this moment as a vote for reflection, because I don't actually think reflection is a good thing anyway. I was just curious for like an academic.
Yeah, methods the same. We get rid of them if they're not used. So short of including everything.
As a point of comparison, like ProGuard does a similar optimization for the JVM, and they let you do both annotation-based like opt-in as well as XML-based opt-in. So anyone can say, I want to, please don't rename this class, or please don't eliminate this method. So that's like what the status quo is on the JVM.
Yeah, Feynman?
So when I'm writing Scala.js code and I reference this, how does is the semantics of that like the JavaScript semantics where it's the execution context, or is it the Scala one, and how does that handle?
So the question was, if you reference this in Scala code that you write in Scala.js, what's the semantics? Is this the JavaScript this semantics, or it's the Scala this semantics? This always, in Scala.js, always refers to the Scala this. If you need to refer to the JavaScript this, there is this thing we call a this function, where basically inside the function you're getting the this as an additional argument. Right? So with this function that takes an integer and returns a string, inside would actually have two arguments. It would have the this and the integer, and you will have to return a string. Right? So there is access to this, but by default, we're being very careful that we respect Scala semantics, so that this has Scala-style this semantics. Other questions? Yeah, I guess, yeah, thanks. You want the shame slide? All right, she calls me out. All right. So on the left here, we have stuff which is there in general. So I titled it IR, so it's really stuff that carries over the whole pipeline. We have things that are different in the compiler, and there are things that are different in the linker. So the first really big thing is hijack classes. Some of the classes, the best example is Java long string. Right? As far as Java is concerned, a string is just a class. Right? We're not really happy with that, because we kind of want to use JavaScript strings to represent strings. So the whole pipeline knows that, well, if someone says Java long string, what it actually means is JavaScript string. There is actually a type for string in the IR, right? And that's kind of strange, because string is actually a subtype of char sequence. So if you see a char sequence somewhere, suddenly this could be just some implementation of char sequence someone wrote, or it could be a string, which is in terms of JavaScript not even an object. So the whole pipeline kind of has to be aware of that and work around it. There are other examples like that, notably boxes, Java long integer, Java long, and all these kind of things, because we don't box them in Scala.js. We just pass normal integers around, which is nice. There's more types in the IR. There's the string type. There's a couple of types that Scala has internally, and we could just make types out of them. And then on the JVM, they use like dummy types for them. There's array types, which are actually pretty painful. Right? The JVM has reified array types, so the array knows the type of its inner element. That's not the case in JavaScript. And there's record types. Record types, they don't live in the files. They're helper types when we do class inlining. We actually allow, for scalar inlining, is what some people call it, if you have a class, a small tuple somewhere, and you can inline all the methods you call on that tuple. you can actually be inlined at the fields of the tuple, rather than creating an actual tuple class. Labeled blocks. Class files actually support gotos. And the Scala compiler creates gotos for pattern matches and tail recursive methods. So the Scala.js compiler backend actually has to recognize these patterns and translate them back into a more higher level structure. And sometimes when you have very crazy macro libraries, the backend crashes. It's like, hey, I don't know about this structure. So you have to change your macro, wait for a version until we fix it. Modules, or aka objects, they, I mean, as in when you write object something in Scala, we actually have these in the IR, whereas Scala class files don't. The compiler, it special cases Scala enumeration because it needs reflection to work, which we don't support. So all the code that uses enumerations wouldn't work. So the most basic cases of enumerations, we actually do some magic that you can recognize the names, that you still have the reified runtime names of the fields. Reflective calls, we support them, but we need kind of some magic to make them equally broken than they're on the JVM. Function literals, how do you write a JavaScript function literal? There's actually a lot of like boxing and unboxing and going back and forth. And export overloading, right? I mentioned that exports can actually be overloaded, and we do dispatch based on the runtime type of the arguments. So it's not the static dispatch you would have on the JVM, but you basically do type checking, right? The argument comes in, it's like, oh, is this an int? Oh, yeah, okay, so let's call the int method. Oh, this is string. Oh, let's call the int version, the string version, right? Or like, oh, no, this is not. Like, hey, oh, this is 2 arguments. All right, so it's this completely other overload over there, all right? In the linker, I completely enacted instance tests, right? Because if I give you a value and say, hey, is this an instance of this interface? I said interfaces are erased. Well, then you can't reply to that. But a lot of Scala code relies on that, notably pattern matching, which is kind of important. So yeah, we need to basically carry runtime type information around to do that, which I guess is fine. Longs. JavaScript does not do longs. So the linker replaces the primitive type longs by a class of ours, which has 3 fields, high, mid, and low, which are each of them an integer. And well, if you compose them, they're long. If you want your Scala.js code to be fast, a word of advice, don't use longs. I didn't touch on the whole inheritance in JavaScript story, right? So especially this slide here, this is actually not the full picture. Each class has 2 constructors. One is the actual constructor, and one is the constructor you can inherit from, which is common practice in JavaScript. And we also have the init method. That's just how on the JVM, the constructor actually just allocates fields. The actual constructor and the init methods does what you as a programmer would consider to be the constructor, right? So this guy here would actually just assign null, which is the default value for an object to messages $1. And then you would call, each time you instantiate a multi-editor, you would call new multi-editor dot underscore underscore, no, init underscore underscore underscore, which is the magic name we have for constructors. Yeah, so this is a bit more complicated in there. And then semantics and output modes. The linker supports just emitting something to ECMAScript 6. So you can just flip a switch. Now we actually emit ES6 classes. The linker has both of these, ECMAScript 6 and strong mode are experimental. Strong mode is strict mode on steroids for JavaScript people that V8 is coming up with. So they're basically just trying to limit JavaScript to even more language constructs so that the VM can be even more efficient. You could just flip the switch and you have strong mode support, which currently is slower than ECMAScript 5, which is kind of funny. Yeah, the semantics are basically, you can tell the linker to get completely rid of as instance offs because they're too slow. Right? The JVM is good at optimizing as instance offs. JavaScript is not, because they're not really a concept that exists for these guys. So sometimes there's just forks in there and different ways to emit the same thing and basically say, oh, hey, actually erase all that. Another flag is strict floats. If you have a float, I think that actually is kind of the same on the JVM. You can say, hey, a float might actually also be a double. It might be more precise or not. Right? Or you can say I want strict floats. And if you say strict floats, well, you'll get a float, but it's potentially slower. Because if the JavaScript runtime is older, it doesn't support the relevant float methods, notably fround. Yeah, and that potentially just, I mean, try and round a double to a float in user space when you don't have access to the individual bits. That's what's going to happen. So you might not want that to happen unless you really have to. Yeah. More questions? All right, I guess that's it. Thanks a lot.